So we're going to work in section 4.3, which is going to start combining some of the things we've been learning about derivatives with the graphs of these functions. In particular, I'm going to work with f of x equals x to the fourth times x minus 1 cubed. And what I really want you to get out of this is a little trick about factoring the derivative. So let's work on finding that value, finding the derivative. One thing you should notice about this is that you're going to have to use a product rule. You've got an f times a g or a u times a v if you'd like to do it that way. So let's work on that with the product rule. F prime of x is going to be the derivative of the first. So it's going to be 4x cubed times the second, x minus 1 cubed, plus the derivative of the second times the first. Now the derivative of the second, you kind of got to use a chain rule. So when I differentiate that, the 3 is going to come out in front. I'll still have an x to the fourth. X minus 1 squared, lower that from the exponent, times the derivative of what's inside. What's the derivative of the inside?
1.
1, yeah. But I want to remind you that you do have to use a chain rule there. The derivative is 1, that works out great. The thing is, with this, you got to spend a little time cleaning it up so you can factor it. And let me suggest a way to do that. Here and here, I have some common factors that I can pull together. And I don't know how well the yellow is going to show up on this, but here and here, there's also some common factors. What I suggest is you factor those out. So how many x's can I factor out? What's in common amongst the x's?
3.
3 of them. So x cubed. And then I'm going to have x minus 1. How many x minus 1s can I take out?
2.
2. Thank you, AC. Now, let's think about what that leaves behind. I'm leaving behind a 4. Took out all the x's. And I took out 2 of these. So it's going to leave behind 4 times x minus 1 to the first power. Okay, that's fine. Let's figure out what I'm leaving behind from this one. Well, I didn't take out the 3, so 3 is there. I took out 3 of the x's, so there's an x there. Both of these came out, so just a 3x. How's that look? So far, so good? We're almost done with this. All we have to do is clean this up a little bit. If I distribute the 4, I get 4x minus 4 plus 3x, so that's going to be a total of 7x minus 4. So let's do this. X cubed, x minus 1 squared, 4x minus, excuse me, 7x minus 4. There we go, never happened, 7x minus 4. Now we went through a lot of work to do that, to get this all set up. Why do you suppose we did that? What was the purpose of doing all that work just to get it nice and neat and tidy? That's a good question. Well, let's take a look at the graph. So the link that I sent you has this graph on it, and the graph looks kind of unremarkable, doesn't it? Looks pretty flat here around 0. Now, for whatever reason, I've got this scaled in units of pi. Let me just make that a 1 here. So that looks a little bit easier to read. But still, it looks pretty unremarkable. But we know a little bit about this based on the factorization. Now, one of the things we look for are critical points. How do you find critical points of a graph? What is a critical point defined as? It's where the derivative does what?
Doesn't exist.
0.
Equals 0 or doesn't exist, right? So in our case, if we set that equal to 0, the nice thing is that it's already factored, right? And we can pretty easily see where this is equal to 0. Let's work on that. So here, and here. I've got this times this times this. All of that equals 0. Now, the nice thing about the zero product property is that when you have a product of things that equals 0, you know that at least one of them has to be 0. So either x cubed equals 0, or x minus 1 squared equals 0, or 7x minus 4 equals 0. All of these are easier to solve than, say, a 6th degree equation up here. So here it's x equals 0, here it's x equals 1, here it's x equals 4/7. So there should be 3 critical points, 3 mins or maxes in this, right? I mean, that's what the calculus is telling us, but Decimal seems to be telling us something different, doesn't it? Decimal seems to be telling us that it's just a flat, boring function. But I trust the calculus more than I do Decimals. So what I'm going to do, and you can do it too, is if you press the Shift key and put your cursor on the y-axis, you can use your scroll to kind of zoom out a little bit, or to zoom in a little bit. And notice the scale here. I'm zoomed in considerably because this is 0 to 0.2. And I start to see a little bit of a contour here. And I can zoom in some more, and some more, and I'm finally starting to see the shape. But of course, it takes a lot of zooming in. Let's kind of zoom in along the x-axis a little bit as well. It takes a lot of zooming in before you really see the shape of this function, right? And now we can start to make sense out of what we got. Let's look back here at what we got. We got 3 answers, 0, 1, and 4/7. So you should see either a min or a max at those points. Well, here's one at 0. Here's one at 1. And here's one someplace else. And my guess is if we took out a calculator and calculated 4/7, you'd get pretty close to this number. So nice. Now 1 turns out, is 1 a minimum or a maximum? Is this a min or a max? Because I mean, that's a relative max, that's a relative min. No, something different's happening here. That's an inflection point. That's where the graph changes its concavity. So we can pick that up based on our work with the second derivative, but that's okay. It's still a point of interest. And you can still see that the tangent line at that point would be horizontal. Right? It has a slope of 0. So far so good with this. Now on your handout, I actually gave you the second derivative because, you know, spending time differentiating and factoring and stuff like that is going to take a little while. So here's the second derivative. We got f double prime of x is 6x squared times x minus 1 times 7x squared minus 8x plus 2.
Would you be able to drop the handout in the chat again?
It's online. It's on D2L.
Oh, okay.
Yeah. So same kind of thing here. We're looking to find where this is equal to 0. And that's going to mean one of these things has to be 0. So either this is 0, 6x squared equals 0, x minus 1 equals 0, or 7x squared minus 8x plus 2 equals 0. So we can see where this one's equal to 0. That's x equals 0. This is x equal 1. And this one's just a big mess. You can solve with the quadratic formula. Negative of -8 plus or minus the square root of 8 squared minus 4 times 7 times 2 all over 2 times 7. I'm going to get a couple answers out of this that just aren't terribly pretty, but it's going to be places where the function should be changing concavity, or it could change concavity. So let's take a look here. here's the first one. Now, once you've done the first one on your graphing calculator, kind of a neat trick is to go back up and select this, and then just go back and change what you need to change. In this case, for me, I want the negative solution as well. So you get two solutions, one at about 0.77 and one at about 0.37. Awesome. Let's put all these things together, see if we can't make some sense out of this function. So what I like to do is I like to draw little tables of these things. So let's start with the first derivative. So let's make ourselves a little table here to try and organize this information. X, F, F prime. And then there was three places where the function changed signs. One was at 0, the other was at 4/7, and the other was at 1. So if we line these up a little bit, gather some more information, then we should be able to tell a lot about the function. Now, all these points are places where the derivative is 0. But in between, we need to figure out, well, what's happening with the function? Is the derivative positive? Is it negative? What's going on? So what I would recommend is that either with Desmos or with your graphing calculator, you plug in the derivative, and we're going to test points to the left of 0, between 0 and 4/7, between 4/7 and 1, to the right of 1, and see what the sign of the derivative is. Because if the sign of the derivative is positive, what does that tell you about the function there? It tells you that the function is
increasing.
Increasing. Well done. So let me put that one in here. It's quite a crazy function. I'll put it in the factored form. You can put it in any form you want, but the factored form seems to be the easiest for me. So x cubed. I don't need a, oh, excuse me, I do need to exit the exponent there, but I don't need a times there. It understands that the times is implied. X minus 1 raised to the second power. So I'll just hit the squared key. And then 7x minus 4. Now, typically speaking, you expect these things to alternate, but they don't always because of this, square terms like that. So I'm not sure that I expect it to alternate. Let's do a table here. Just to remind you, table setup should be set so that you have independent set to ask, dependent set to auto. I'll delete these values here. And now we need some test points. So what would those test points be? I need something to the left of 0. So
-1.
Yeah, -1 sounds like a good one to me. Thank you. So -1. And then let's go say 0.1 or 0.2. 0.2 should be good. That's going to be between 0 and 4/7. Something between 4/7 and 1, say about 0.8, and then maybe 2. So kind of an odd pattern here, not exactly what we typically see, but that's okay. All we really need here are the signs from these things. So it's going to go positive, negative, positive, and positive. So let's go back here. So that's the information I need here. That tells me the function is increasing, decreasing, increasing, and increasing again. Now the mirror shape of this really seems to indicate what's going on at that point. I mean, without even looking at the graph, what can you tell me about the point at x equals 0?
It's a maximum.
Yeah, that's a relative maximum. Perfect. And then what's going on with the point at 4/7? Somebody
It's a
make
relative minimum.
Yep. So we got a relative max and a relative min. And this turns out to be an inflection point. That's okay. So what's going to happen here is the concavity is changing, but not anything else. So I'll just label it IP, etc.
And that's because of the signs on either side of it, right?
Yeah, I mean, it's increasing and then it's increasing again. So it paused for a second. And let me look at the graph here. Actually, do it here. You see that it was increasing, did a brief pause, and then kept increasing. So it's not a max, it's not a min, it's neither. But the shape of the graph went from concave down to concave up. And we should see that when we further test this in the second derivative. Okay, how are we looking on that one? Let's finish this up. We can play around with the second derivative as well. So I'm going to make the same kind of a chart for the second derivative. Come on. So let's see, what points do we need there? We need 0, 1, and those two ugly ones. So X, F, F double prime. Let's see if we can't put these in order. 0, 0.37, 0.77, and 1. So apparently a lot of changes in concavity, or at least potential for a lot of changes in concavity. Okay, so the second derivative is 0 at all of these. That's okay. If the derivative doesn't exist at a point, it could still change concavity around that point. So you should probably be doing those testing of points either way. Now, I get the joy of plugging in yet another crazy function into my calculator. This one's even crazier than the last. Let's see. We got 6x squared times x minus 1. This time it's just to the first power. And then here I need a 7x squared minus 8x plus 2. And let's do some testing of points. Let's go up to the table. I'll clear out all these old points. And kind of like before, we need to test to the left of 0. So I'll just pick -1 and then say 0.2, 0.4, 0.8, and 2. And wow, this is a nice alternating pattern. It's what we typically see. It's what my algebra students often see when they're doing those kinds of problems. Their math 1150 and 1540 classes. So let's see, it starts out negative. Actually, you know what? We got negative and then negative. Why would that not change signs there? Oh, okay, because 0 is a square. All right, so it doesn't quite alternate. So it's negative, negative, positive, negative, and positive. Yeah, around that squared term, the square terms kind of mess things up. That's why you're not getting a change in sign there. But This is telling us something different. The fact that the second derivative is negative tells us something about the shape of the graph here. We're no longer working about increasing and decreasing, where it's concave up or concave down. Which one is this? Concave, down, down, up, down, up. And we should see that match the graph. So once you have these charts made, you can fill in stuff like, concave down on negative infinity to 0, union 0 to about 0.37, and union 0.77 to 1. That's where it's concave down. It's going to be concave up on the other intervals. So 0.37 to 0.77. This is just my symbol, union. WebAssign would have you use a comma here. I'm just using a math symbol just because of my training. And then finally 1 to infinity. Let's see if this matches what we see in the graph. In particular, 1 to infinity, 0.37 to 0.77. Does it match? Does it seem to make sense with what we're seeing on the graph? So, all right. So let me just put in this point. Let's see, we want 0.37 and h of 0.37. Okay, so what happens here? The function changes from being concave down to concave up, and it's going to be concave up until we get to the next inflection point, and that's going to be at 0.77 and h of 0.77. That looks reasonable. It's certainly got a concave up shape here. Now, to determine where it exactly changes concavity, that's why we need the calculus. All right, and the calculus is telling us that this is an inflection point because you're changing from concave down to concave up. This one is an inflection point. Again, change in concavity, concave up to concave down. And this last one's an inflection point. Concave down to concave up. And you can see that easily on the graph. So that one's pretty easy to see. The exact point where these would be inflection points, those are harder to see. Again, you need the calculus there. Okay, good one. Question.
So on like the test or whatever, are we gonna have to graph this, or will it just like be asking where it's concave up and down, whatever?
So there's a couple ways that they could ask these problems. I've seen them, give you intervals and you choose whichever one. But, and it's a great question. What I'd like from you when I look at your work is I want to see calculus. I mean, I have no problem with you checking it on the graphing calculator or on decimals or something like that. But in the end, it should match the calculus that you have on your paper. So it's a great way to double check your work, but you shouldn't rely on it completely. This is a class in calculus, and I do want to see some calculus work, but there's no problem with graphing it. Use the technology, make sure that you've got it right, all right?
All right, that's what I wanted to hear, thank you.
Yeah, hey, appreciate the question. So let me see here. L'Hopital's rule. I was trying to find example. So like here's one that we're gonna have to do. That we'll do. I want to do one more before we get here, but you actually have to put in exact values. Whereas there was one. There's another one someplace that trying to. What happened to it? There's another one that we did that we're going to look at. Maybe it's in section 4.5 that they just give you a bunch of things to select from. So there'll be some more answer to that question, more clarification for you coming up, Finn. Anything else on this one? All right, well, tell you what, let's take this kind of as like a little guide and apply it to a problem that you could see in WebAssign. In fact, that I took from WebAssign. And it's this one. So it says sketch the graph of a function that satisfies all of the given conditions. Well, let's start out with the fact that they're telling us that the derivative is equal to 0 at certain points. So that means there's going to be mins or maxes at these points. So I'll call this maybe example B. And we'll just kind of organize the information that we see a little bit more. So I'm going to make one of those charts that I did just a minute ago for the first and second derivatives. We've got points at 0, 2, and 4. So 0, 2, and 4, that's where the derivative is 0. So I want to take note of that. So it tells me that there's something interesting happening at these points. Either there's a relative max, a relative min, or an inflection point. We'll have to see. But that's a good place to start. Let's see what else they tell us. They tell us that the first derivative is greater than 0 if x is less than 0. So to the left of this, I'm going to put a plus, because the first derivative is greater than 0 when x is less than 0. It's also greater than 0 between 2 and 4. So I'll put another little plus between 2 and 4. So right here, and we're looking okay. When we look back here, it now tells us that the first derivative is less than 0 if x is between 0 and 2 and greater than 4. So a typical alternating pattern for the signs of the derivative, plus, minus, plus, minus. So that's telling me that the function's increasing, decreasing, increasing, and decreasing. They also give us some information about the second derivative. So the second derivative is greater than 0 for x between 1 and 3, and less than 0 outside of that interval. So I'm going to do a table with some more values here. So x, f, f double prime, 1, and 3. And just to keep you up on what I'm doing here, let me switch screens. Now, I'm not sure they actually told us what's happening with the second derivative at these points. Don't know, but that's okay. Let's fill in what's happening around these points with the second derivative. So to the left, it's going to be between 1 and 3. The second derivative is positive. And that I'm getting from this right here. Second derivative is greater than 0 for x between 1 and 3. It's less than 0 if x is to the left of 1 or to the right of 3. So to the left of 1 or to the right of 3, it's negative. And that tells me that the function is concave down here, concave up, concave down. All right. Notice the concavity doesn't necessarily match, you know, where your mins and maxes are. That's okay, it doesn't have to. In fact, in terms of mins and maxes, what kind of a point is 0 going to be? A relative
Maximum.
max, thank you. Because you're going up and then you start going down, so that's a max. And then conversely, going down, then start going up, it's a relative min. And finally, a relative max. And these are both inflection points. Someone tell me why these are inflection points. What about our little chart here tells me that they're inflection points?
The sign and concavity changes on either side of them.
Yep. So a change in the sign reflects a change in the concavity. So where the function changes concavity, that's an inflection point. So let's take all this information and see if we can't figure out which graph is which. So you're expecting something that's, you know, kind of parallels this. Concave up and then concave down, and something like that. So that's roughly what we would expect. Let's see what our choices are. Well, I'm thinking we can eliminate the first one here, right? That one's not the right one. So scratch you. Because this one doesn't start with a relative max at x equals 0. This one starts at a relative min. So, okay. What other one could we eliminate? Well, let's see here. I think this has too much going on here. All right, I mean, you do have a relative max at 0, relative min at 2, relative max at 4. This still could be in the running. All right, so we only got lucky with one. There's only one function that just clearly isn't the right one. Let's take a look at the others and see if we can't be a little bit more shrewd with eliminating things. So I'm looking for a relative min at 2. So we got a relative min at 2 there, and a relative min at 2 there, and a relative min at 2 there. So we're okay with those. They all have relative maxes at 0. So we're okay with those. Let's see. And then at 4, we have another relative max. Okay. So that's here. Boy, I don't think we can eliminate any of these, can we? Usually, we can eliminate one. Why can I eliminate this one?
Because it doesn't finish going down.
Yeah, it doesn't have a maximum, a relative max at 4. So good job, Aiden. Thank you. So now we're down to these two. What's left to use to make our decision? Well, we can take a look at our inflection points. And we're supposed to have inflection points at 1 and 3. The concavity is going to change. So, all right, let's see. At x equal 1 and at x equal 3, that looks pretty reasonable. So let's think. What are we expecting? We're expecting a concave down, concave up, concave down kind of shape. And those inflection points are going to be at 1 and 3. Does this look reasonable?
Yes.
Has it knocked itself out of the running yet? No. No, it hasn't. That one's still in the running. All right, looks like you got some inflection points here. How about here? Well, we got what could be an inflection point at 1, another one at 3. But there is a little problem with this graph. Can anyone tell me what the problem with this graph is that kind of eliminates it from the running? Why can't it be this one?
The beginning and end.
Yeah, the beginning and end start to change a little bit. I mean, at some point, I'm not sure where, maybe about here, the function is going to be concave up again, right? But it didn't say that in the problem. Likewise over here, we've got another interval where the function's concave up. And that's not part of the given information. For us, it was concave down if you're to the left of 0, and that's it. It doesn't come back up. So this is the only one that satisfies all those criteria. It has to be concave down forever, to the left of 1 and to the right of 3. And this one is. So that one gets a check mark. This one doesn't quite, because it does eventually become concave up. Whew. All right. So a good one. And just so you know, on an exam, if it was a multiple choice like this, I'd probably only give you one shot. I just don't think that it tells me much that you can get it right out of 2 tries. And you can probably eliminate enough, so 2 tries will give you enough. So make sure that on an exam, you get it right the first time. Good one. Other questions on that one? There's another example that I want to do that has some fancy factoring. And it's what I call problem 43-ish on your handout. So this one, h of x is x times 8 minus the square root of 8 minus x. So let's look at that one. Example C. All right. And we're only going to look at the first derivative this time. Second derivative is always going to be less than 0, so we'll be okay there, I think. H of x is x times the square root of 8 minus x. Now the square root's a nice symbol. I remember looking at some old math scripts one time, and they just had the most bizarre notation for things like square roots. And I'm so glad we use one here. But unfortunately, using it here isn't as convenient as it could be. So for purposes of differentiation, you might want to think of it as 8 minus x to the 1/2 power. That's your u times v. You've got to use the product rule to differentiate this. So h prime of x is going to be u prime, which is 1, times 8 minus x to the 1/2 plus v prime. Let's stop and think together what v prime is going to involve. It's going to be the derivative of this term. So it's going to be 1/2 times 8 minus x. What's 1/2 minus 1?
Negative 1/2.
Negative 1/2. Am I good there? Did I finish differentiating this?
Inside is left.
Yeah, well done. Thank you, AC. Times the root of the inside, which is your -1. Don't forget the x here. This is kind of a big mess, so let me clean it up a little bit. I'm going to take the negative and the x and put them up top here and get 8 minus x to the 1/2 minus x over 2 times 8 minus x to the -1/2. Now you're going to see some factorization like this again later, but let me show you this trick because it does come up. When you're working with something like this, you want to factor out the largest negative exponent. Now in this case, there's only one. When you do problem 30 in section 4.5, there's going to be 2. But for now, there's only 1. So I want to factor out that term. So I'm going to factor out 8 minus x to the -1/2. Now you may not realize it, but when you do some factoring, what's happening is you're really dividing each term by that factor. So let me just show you a little bit on some scrap paper here. If I add 4x plus 20 and I ask you to factor it, everybody could factor it as, oh, that's 4 times x plus 5. Well, what's really going on is when you factor it, you're dividing each term by that factor. 4x over 4, oh yeah, the 4 is canceled. 4 goes into 25 times, no big deal. And for the most part, it's fine doing it in your head. But with these, it gets a little tricky. I'll show it to you the long way once. If you need to do it this way or not, it's up to you. But I'm going to divide each of those 8 minus x to the 1/2, and then minus x over 2, 8 minus x to the negative 1/2 by this term that I'm factoring out. So 8 minus x to the negative 1/2 and 8 minus x to the negative 1/2 again. So the trick was I chose this term. It's the largest negative exponent. I'm going to factor that out. But I'm going to get a lot of simplification here, a lot of really nice simplification that you want. So let's see what happens here when we factor that. And let me get that back on screen here. So the 8 minus x to the negative 1/2 term is going to be out front. Let's start here with the easy part. Call it the easy part because something nice is going to happen there. That whole term is going to cancel itself out. So that leaves me with just that little piece right here. So minus x over 2. How about here? Well, when you divide things with the same base, what happens with their exponents? If I add x to the 8th over x to the 3rd, what do you do with the exponents?
Don't you subtract?
You subtract, so I get x to the 5th. But the thing is, if one of these exponents was negative, x to the 8th over x to the negative 3rd, when you subtract, it's like addition, right? Negative of negative 3. So you get x to the 11th. The same thing's going to happen here. When you subtract those things, the negatives are, you're going to get 1/2 minus negative 1/2. Can anyone do that in their head?
1.
1. And isn't that nice? That ugly term turned into a 1. So there's going to be 2 last things I'm going to do. I'll pause here for a second because I know that that's perhaps a tricky and uncomfortable factorization. If there's some place that I can add some more details to help you out, let me know. Doing okay here? I mean, this is stuff that I'd like to see on your papers when you do these things. All right. This and this are like terms. That has a sign of -1. That has a sign of -1/2. So -1 and -1/2 give me a -3/2 total. So this is going to be 8 minus 3/2 x. This term I'm going to bring into the denominator. 8 minus x. When I bring it to the denominator, what happens to the exponent?
Positive.
Yeah, it's positive, changes to a positive 1/2. So a lot of work here, but that's your h prime of x. we can now find the critical points. There's going to be 2 of them. Now, one thing that you could have noticed, and perhaps I should have helped you out with at the start here, this has to be positive or 0. So that means 8 has to be greater than or equal to x. In other words, your domain is everything up to 8, up to and including 8. So anything less than or equal to 8, negative infinity to 8, that's part of your domain. Why do I mention that? Well, 8 is part of your domain, but if you're looking for critical points, those are going to be where h prime of x equals 0 or h prime of x does not exist. The equals 0 part is easy. That's just going to be where the numerator equals 0. Because where the numerator equals 0, the whole fraction is going to equal 0. So let's do that. H prime of x equals 0 equals 8 minus 3/2 x, like that. A lot of you don't like fractions, so let me get rid of them. I'll multiply everything by 2. 2 times 0 is 0. 16 minus the 2's will cancel. 3x. Moving to the other side, I end up with x equals 16/3. Yay. How about where h prime of x does not exist? Where would it not exist?
Where the denominator equals 0.
Where the denominator equals 0. H prime of x does not exist where 8 minus x to the 1/2 equals 0. If you square both sides, you get 8 minus x equals 0 or 8 equals x. So that's where the derivative is 0. Or excuse me, the derivative is undefined. Sorry. You can make a little chart here. I hesitate to put in 8 because 8's at the edge of your domain, but I'll put it in for sake of completeness. The derivative does not exist at 8. And we'll see if we can't figure out why the derivative doesn't exist there. But we do have 16/3 as a critical point. Derivative 0 here. And I'm not going to take the time to take out a calculator and do the testing of points. Let me just do it for you mentally. So you test points to the left of 16/3. Test them in the derivative like 0. If you put in 0, you get something positive. If you put in something bigger than 16/3, you're going to get something negative. So the function's increasing, then decreasing. And then you've got this oddball of what's happening here. All right. Let's compare that to what we see about the graph. Before I look at the graph, any second thoughts here or something that maybe I went over a little bit too fast? So the graph I'm hoping is one of those links on Desmos that I sent you. So let me click over to here. I'm going to shut off this graph from the last one. We'll turn on this one. And oh my, we got to zoom out a little bit. It might be easiest just to hit the default zoom at home. And there we go. That kind of cleans things up a little bit. What's nice is that if you're doing this on Desmos, you can easily trace and find that maximum point. It's right where we said it was, 16/3. If you plug in 16/3 for x, you get about 8.709 for the y value. The function is increasing until it gets to this point, then it's decreasing. Looks perfect. It's always concave down. You could prove that with the second derivative. The second derivative will always be negative. But can anyone make sense out of this here? How come the derivative didn't exist at 8? I mean, we don't get any change in sign because the function just ends at 8. So, you know, I put it in there for completeness, but why doesn't the derivative exist at 8? Can anyone fill that in for me?
Can't take the square root of 0.
Yeah, that's true. Well, no, you can take the square root of 0, but you can't divide by 0. So that's numerically what's happening. It's algebraically what's happening. But in terms of the geometry, why doesn't the derivative exist here? What's going on? Can anyone figure that out?
Is there a vertical tangent there? Or?
Yeah, well done, Matt. Yeah, there's a vertical tangent here, right? I mean, you take a look at the rate of change of that function, you'd have a vertical line there. So x equals 8, right there. Beautiful. So a vertical line has an undefined slope, which is why the derivative doesn't exist at that point. So, all right, thank you, gentlemen. Any other comments or thoughts on this one? Okay. All right, I think that's all I got for this section. So we'll take a pause here. So I guess we can't complete section 4.3 until we do one example that has some trigonometry involved. That would be this one. So 3 sine of x plus 3 cosine of x on the interval 0 to 2 pi. So with that restriction, graph looks like what we have here on Desmos. So let's see what our graph, let's see what the calculus tells us about that little portion of the graph. Now I'm going to start by finding the derivative. Derivative is going to be pretty straightforward. So this is going to be 3 times derivative of sine, which is cosine. What happens when you differentiate cosine? What's the derivative of the cosine?
Negative sign.
Negative sign. So I'll get minus 3 times sine of x. Now sine and cosine are defined everywhere. So I'm not going to find a place where the derivative is not equal to, or excuse me, is undefined, but I can find a place where it's equal to 0. Let's move the 3 sine x term to the other side. I get 3 cosine of x equals 3 sine of x. And there's a little bit of a trick here that maybe you picked up in your trigonometry class. To solve something like this, what I would do is divide both sides by 3 cosine of x, 3 cosine of x. On the left-hand side of this, what do I get?
1.
A 1. And on the right-hand side, the 3's cancel, and I'm left with sine over cosine. Another term for sine over cosine would be what?
Tangent.
Tangent. So basically, I want to know where the tangent is equal to 1. Now, if you're scratching your head going like, oh yeah, that's familiar, but trig was so long ago, no problem. What we're going to do is we're going to do the inverse tangent of 1, and that'll be equal to x. So the inverse tangent of 1, now let's do that on our calculator. But you're probably not going to recognize the number that you get if your calculator is in radian mode. And I know calculus is done in degrees, but for this one, I'm just going to put it in radian mode just for a minute. Let's clear out all this stuff. Clear again. So the inverse tangent of 1, anyone want to guess before I plug this in?
5/4.
So pi over 4, yeah. So 45 degrees, it's like, oh yeah, 45 degrees, pi over 4. Yeah, that's it. Now, there's actually a couple places where tangent is equal to 1. Tangent is equal to 1 at pi over 4, but tangent is also periodic with period pi. So if I move a distance of pi around the unit circle, I'll see another place at 5 pi over 4. So these 2 points, pi over 4 and 5 pi over 4, are places where the tangent will equal 1, or more importantly, where the derivative is going to equal 0. So x could equal pi over 4 or 5 pi over 4. Let's put that aside for a moment and continue working with the second derivative. So the second derivative is going to be minus 3 times sine of x minus 3 times cosine of x. And we'll set that equal to 0. It's going to be kind of a similar game to the last one. If I move one of these to the other side, I get minus 3 sine of x equals positive 3 cosine of x. This time I'm going to divide by 3 cosine of x and get a negative 1. Actually, you know what? Able to divide both sides by negative 3. Yeah, because I want to cancel out the negative there. So I'll divide by negative 3 cosine of x on both sides. That cancels out the negative here, leaving me with tangent of x equals negative 1. And again, that's going to have 2 solutions. You're going to have solutions at 3 pi over 4 and 7 pi over 4. So right here, tangent is going to be negative 1, and again down here. So x equals 3 pi over 4 or 7 pi over 4. The rest of this is just testing some points, making sure that the mins and maxes are what you would guess them to be. So let's do a little table like we've done with the rest of our problems. X, F, and F prime. Then let's see, pi over 4 and 5 pi over 4. Likewise, let me do a little table over here for the second derivative. X, F, F double prime, 3 pi over 4 and 7 pi over 4. Now, I've shown you how to set up some tables in the graphing calculator. You want me to spend a minute or so doing a table on Desmos, or should we just do it on the graphing calculator? Doesn't matter to me.
Graphing calculator.
Graphing calculator works. All right. Let's put our calculator back in radian mode. Maybe you guys didn't switch. I did. So I'll put that in radian mode. And I'm going to enter the first derivative, which is 3 cosine of x.
Why did you use degrees for the last problem?
I just used degrees briefly because I needed to figure out where the tangent was equal to 1. Now, there's a lot of ways you could do that. If you did the inverse tangent, if you're looking at that and going, all right, calculator, help me out. If you did the inverse tangent in radians, it probably wouldn't register with you what that was. Let me finish typing in this function. So this could be 3 cosine of x minus 3 sine of x. I could have factored out the 3, but I was just being lazy, I guess. But let me go back and answer your question here. So this is now in degrees, or excuse me, now in radians. So when I do this, I'm going to get pi over 4, but it's going to be in radians. But it just gives me a decimal value. It doesn't give me that nice, neat pi over 4. So the question is, would you recognize that Oh yeah, 0.785. Yeah, that's pi over 4. I wouldn't.
Okay, thank you.
So it's, yeah, so it's just easier to see this in degrees and then convert it to radians rather than just try and work with radians. I mean, there's
Yeah.
other things you can do, but it's, I don't know. I think you get my point here though.
Yeah, thank you.
Yeah, thank you. Okay, so let's do ourselves a favor here. There. And here. So we got to test some points. Now, I guess test points, we got to choose, you got to want to think a little bit clever. Let's see. So for the first derivative, let's delete all these points. I can test a point at 0. And then between pi over 4 and 5 pi over 4 would be the point pi. And then I need something greater than 5 pi over 4. Well, let me go all the way up to 2 pi. So, okay, so what's the relevant information I need from this table here, though?
Just the signs, right?
Just the signs. Well done, Matt. So positive, negative, positive. And that tells me that it's increasing, decreasing, and increasing. And likewise, I need to repeat that with the second derivative. So let's plug that in as well. So this time it's going to be minus 3 sine of x minus 3 cosine of x. And like the last one, I'm going to do some test points. I'm not sure I can get away with the same exact, well, actually, you know what? I think I can get away with the same exact test points. Yes, I can. These test points will fit in between these here. And what we saw is that went negative, positive, negative. So it's concave down, concave up, concave down. This tells us pretty much all we need to know about our function.
For the f of prime, is that the last one there? Is that a increasing or decreasing?
F double prime?
No, just f single prime, the last one.
Bring me right there.
Yep.
Yeah, that'd be increasing. Thank you.
Okay, yep.
Yeah, I think that there's a little dust on the lens that probably obscured it. It might have looked like it made a mistake, but it was just dust on the lens. Thanks, Sarah. Increasing, decreasing, concave up, concave down. So a couple things. This would be a relative min, relative max, sorry. Relative max. This would be your relative min. How about this? Is there anything interesting about these points over here? Can I give them a special name too? These would be your inflection points. And then you've got the intervals where it's increasing. So 0 to pi over 4. Web assign, use a comma. And then 5 pi over 4 to 2 pi. Now 2 pi, I think you can use a bracket because it, actually, you know what? No. Parentheses, because at 2 pi, well, I have to take a look back at the graph. Let's take a look back at the graph. 2 pi, you can have a maximum there. No, 2 pi, it's still increasing at 2 pi. So we could actually use a bracket there on 2 pi. And there we go. No, they use a parenthesis on 2 pi. I'd argue you can use a bracket. We're going to use a parenthesis. So the rest of this, you've got intervals on which it's decreasing. Okay, we figured that out. One thing we didn't take the time to figure out was the local min and local max. Now here, when they're looking for local min and local max, they're looking for the y coordinate. They're not looking for the x values. So you have to be a little bit careful. If you just try to plug it in your calculator, it's going to give you a number that you don't recognize, like negative 4.3 or something like that. So to see how you'd get this, get an exact value, let's actually plug that in. Try and find our local max, which is at pi over 4. So f of pi over 4 would be 3 times the sine of pi over 4 plus 3 times the cosine of pi over 4. Now, the interesting thing is that both of these values are the same. Does anyone remember what the sine of pi over 4 is? Square root of 2 over 2. Likewise for the cosine. If you add these together, you get 3 plus 3 is 6 square roots of 2 over 2. And that simplifies to 3 square roots of 2. And that's the exact value. That's what they're going to be looking for when you try and find the relative max and relative min. So the relative min would be the same thing, f of 5 pi over 4. It's just to this time that both the values would be negative. So you end up with negative 3 square roots of 2. Awesome. Comments or questions on that one? Something on that one that maybe you want to look back at, go over a little bit more? Okay, let's call it a day on this section then.